Thanks, Keith. And so thanks to the organizers for inviting me. And I had a hard time figuring out what I could talk about here that would be relevant to you guys. But I came up with this thing, which actually is the first time I talk about it. And so hopefully you'll find it interesting. We're not going into the weeds. I'm at the continuum level, but there's still some really interesting things that come out, as I hope to convince you. So I always like to start with my acknowledgments. So this is joint work with a number of different colleagues. So a longtime collaborator and former student and postdoc of mine, Shuang Li, who's at Illinois Institute of Technology. And then his student and my postdoc, Meng Zhao, collaborator Wenjun Ying, and Pedro Años, who was a postdoc with Shuang. And so I'm going to talk about mainly work in a couple of papers, so they're here, where we're using electric fields to control the morphological instabilities, basically fingering instabilities in Hele-Shaw cells. And so the outline of the talk is going to be an introduction to interface problems and viscous fingering. Then we'll introduce the electric fields and this electro-osmotic flows. We'll do linear stability analysis to get a handle on the system, and then we'll look at the nonlinear behavior through numerical methods. And then I'll end with some conclusions. And so pattern-forming systems are ubiquitous and very important. And there's many examples of the development of ramified patterns that look like viscous fingers. And so viscous fingering is kind of the simplest system to develop patterns, and it still has a lot of important applications, particularly, for example, in oil recovery. That's a standard one. And so the problem is that you have interactions amongst many different length scales, and the systems are highly nonlinear, so it's very hard to predict what's going to happen. And so it's, from a physical point of view, they're rather simple, but you get these amazingly complex patterns that emerge from these simple interactions. And so the Hele-Shaw cell is kind of the simplest pattern-forming system that one could look at least one of the simplest. And so basically the idea is that you have a fluid that's confined between two typically glass plates, and they're closely spaced. And so it's nearly two-dimensional, and that's what gives, at least mathematically, a beautiful simplification. And then what happens is that if you inject, and so here's just a snapshot of in injecting one fluid into another fluid, and if you're injecting a less viscous fluid, so for example air, into a more viscous fluid, such as oil, then what happens as you inject more and more air, the pattern that emerges will become very complex. Highly ramified, and you get these fingers and tip splitting and development of almost fractal-like structures. And so it's really a classic problem for studying, well, interface dynamics and pattern formation. As I mentioned, it has important industrial applications, particularly in oil recovery. Just to kind of show you so this is just a snapshot, but just to show you what one of these guys would actually look like if you're simulating it. This is the kind of development of this complex pattern that you just saw here. And so as the system is growing, you see these tip splitting events and getting this highly ramified pattern. And so this is a numerical simulation. I think that's the biggest Hele-Shaw bubble in the world. At least it used to be. So what's the problem? The problem is very simple, at least from a mathematical point of view. So by putting the viscous fluids between two glass plates, you can average over the narrow gap and get an effectively 2D problem. And there is a meniscus, and one could take that into account. But I'm not going to do that right now. It will only slightly perturb what I'm talking about. And so the classic, so if the fluid is very viscous, the gap is small, then it's roughly Stokes flow. If you average over the gap, you can get what's known as Darcy's law, so porous media-like flow, where the velocity is generated by gradients in the pressure, and m is hydraulic mobility. And so B is the gap width, and 8 is the viscosity. So just I'm just talking about the exterior problem for the moment. So the viscosity of the exterior fluid. Think of the interior fluid as air. Then the fluid is incompressible, and there's a surface tension at the interface. And so if I'm at the exterior, the pressure, for example, would be a constant here, so the pressure jump is essentially proportional to the curvature, and that proportionality constant is the surface tension. So that's a stabilizing factor. And then what you're doing in these Hele-Shaw cells is you're injecting air. So it's incompressible, but the volume is growing. And so you have a constraint basically on the volume, and it's growing because you've injected fluid into it. And then once you solve these equations, so the velocity is the gradient, is this mobility times the gradient of pressure. That should be, so if I'm just at the exterior problem, then the normal velocity is just the normal component of that. And then once I've determined the velocity, then I move the interface. And here I've divided into a normal component, which is the physical one, and the tangential component, which can be chosen because it doesn't change the shape of the interface. Okay, and so I wanted to just give basically a brief description of the underlying insight as to why there is this instability. Well, one is obviously that you have a less viscous fluid going into a more viscous fluid, so it wants to go in a narrow region. But why does it get more and more complex? Why does the shape get more and more complex? And so the key is that there's an interaction, and the shape is the emergent behavior of this interaction between macroscopic driving forces, so that's the injection flux, and the microscopic interfacial properties, and that would be the surface tension in this very simple problem. And so you can understand this in terms of time scales. So there's a time scale, so if J is the injection flux, so that's basically the rate of area change, because it's 2D, then there's a time scale associated with the flux, which is the size squared. So R0, think that as a characteristic size of one of these bubbles if it were air. And that's R0 squared over J. So that's the time scale associated with injecting fluid. And now at the interface, the simplest thing is to consider surface tension. And so one can construct a surface tension time scale, which is basically the time scale surface tension acts to relax the local system. And so that scales like R0 cubed, and then this surface tension, the hydraulic mobility. And so if you now look at the ratio of those time scales, so the time scale of the associated with the flux versus, so that's the driving force, and the time scale associated to the relaxation, which is the surface tension. If the flux, let's say, were constant and the other parameters are constant, that would decrease like 1 over r, the system size. And so as the system is getting bigger, this ratio is getting smaller. And so that means that the surface tension is having less and less time to act to stabilize the system. And so that's why, as it grows, it becomes less stable. And so that's the origin, essentially, of the Saffman-Taylor instability. But that gives you some insight, because one thing you could think is, well, what happens if I don't take a constant flux? What happens if instead I take a decreasing flux? Well, at least decreasing with respect to the size of the system. And so as the system is growing, I'm reducing the flux. I'm reducing the amount, the injection rate. And if I do it in this way, scale it like 1 over r, then the two, this was the formula we had before, then now the r here cancels with the r there, and I get just this coefficient. And now the two are on the same time scale. And this turns out to be quite insightful, so that you now can use this as a control strategy to actually control the shape of the bubble as it grows. And so the idea is, well, can we control these complex morphologies? And what are some control mechanisms that we can try to do? And so I just mentioned one, at least with the idea. I'll show you that it works, which is this changing the rate of injection, doing that over time. And so that's one way to control or modify the instability. Other ways are you could modify the geometry of the Hele-Shaw cell. So you can use a time-dependent gap width. You could taper the walls, so instead of being parallel, they're tapered. And you could actually put elastic walls in there. So all of those have been tried to, as ways to modify or at least control the fingering that emerges from the Saffman-Taylor instability. And then the time-varying fluxes, which dates from quite some time ago, but then we've exploited it as well as now others. And so why does this work? So, well, it works from that very back of the envelope calculation, but let's actually do some math and see how it actually works. And so so what we'll do now is we'll take a circular interface and we'll perturb it. And so we're going to perturb the radius by cosines. And then we can follow through and write an equation for the perturbation relative to the underlying radius of the circle. And so, and then we can, we get a relation for the flux in terms of the radius change, and also a relation between the pressure and the flux. But this is the key formula. So this tells you how the shape evolves. So the key factor is delta is measuring the size of the perturbation. R is the underlying circle. And so because we're injecting fluid, R is growing. And so delta, if we want to see the perturbation, delta should at least grow along with R. Otherwise, if it's growing and the delta is not changing much, then you don't see the perturbation on the size of the circle that's growing. So the shape factor, we call it, is this ratio delta over R. And so when you do the analysis, you can find that this quantity evolves according to this equation. So K is the wave number of the perturbation. J is the injection flux, and JK is a critical flux that just has a specific formula. And so that's related to the, to the wave number like this, and it comes from, this cubic term comes from the surface tension. And so now what you observe is this JK that has a coefficient, which has a specific form, but it's divided by R. And so now you see if J were constant, and so JK is just this fixed number, eventually, because JK decreases like 1 over R, J will get bigger and the modes will grow. So eventually, if the delta, really I should have put a subscript of K, eventually all the modes will grow if the J is constant. And so therefore, if I take now J proportional to 1 over R, then now I'll be able to factor that 1 over R out from both, and I'll have some control. Not all the modes will grow. I can control what modes will grow. And so in particular, if I take J greater than this JK, that's the Saffman-Taylor, especially taking a constant. If I take it equal to the JK, then this mode doesn't change in time. And you could think of that as a self-similar evolution. Or if J is less than JK, then the perturbation will decay and it'll be stable evolution. And so that's the manifestation of that simple scaling argument in terms of the linear stability. And then what we can do is we can actually run a nonlinear code. So I'm going to give you a nonlinear result. I'll tell you about the method a little bit later. but this is what happens. So now I'm going to take a specific form. This is the injection flux, and I'm going to pick a specific coefficient. And what that coefficient is going to guarantee is that mode 6 is going to be the fastest growing mode. And so we can take, I'm kind of giving you the result, but I'm going to show you a simulation first, then we'll go over this. So for a specific initial condition, that's kind of complex. Let me get there we go. That's the evolution. And it goes nicely to the 6th mode as we would have hoped from the linear theory. This came from the linear theory. And we can then say, well, that was one specific initial condition. It turns out that was the red one, even though I colored it blue over here. But you can take different initial conditions, and they'll all go to the 6-fold shape. And this is a plot of the shape perturbation. So that's the delta over R, but measured from the nonlinear solution, as a function of the equivalent radius, the effective radius of the drop. And you can see we start from some different initial conditions. These different colors are corresponding to different initial conditions that are basically containing different numbers of modes in there. And so what you can see is while they grow at early times, which means relatively small radius, they'll eventually settle down to a constant, which is this a characteristic of this shape. And so once they've gotten over here, then they've reached this limiting shape. You can show they're just rotation. These are the same, but this is just a rotated shape versus that. And so they all go to the same shape. And so these limiting shapes are attractive and stable. Now, of course, there's some time it takes, or at least you have to get big, and you could look at this guy and say, whoa, that's pretty big, right? That's the effective radius. Okay, this is non-dimensional, so we have to scale it, but still it's big. Okay, well, that was one mode. Oops. What about others? So now what you can do is come up with a morphology diagram where we can change that flux coefficient, and we can then look at the symmetry of the limiting shapes. You can find limiting shapes, these attractive limiting shapes, and here they are. So as you step up, increasing in flux, and this is the symmetry, you get this stairwise curve. So these guys all have the same symmetry. The shapes are a little bit different, and these are just some characteristic shapes. But you can basically say, now if I want to get a particular shape, I can choose a flux constant, and I should get that shape, at least that symmetry. Then you can also say, well, how big is the perturbation? These are very nonlinear shapes. They're far from circles. So the linear theory is actually here, the dashed, but the shapes are far from being able to be described by the linear theory. And so you could look at the effective perturbation size, so the shape perturbation size as a function of that flux coefficient. And you see that as you increase the flux coefficient, so you get more fingers, you also get larger perturbations. And in fact, here they get so large, you wonder if they'll pinch off, and we don't know the answer yet for that. But you get very thin necks, for example, here. Up at 10, or maybe that's, yeah, I think that's 9 maybe. Okay, so now, is that just a thought exercise, or can you actually do it? And so we managed, after many tries, we managed to convince some experimentalists to try it. And so Peter Palfy-Moret at the Liquid Crystal Institute was game for doing this. And so he designed a system where, and it's a pressure pump, so we use this linear relation between the pressure and the flux to try to tell them what pressure they needed to get, they needed to inject, prescribe, so that we would have a flux that has this form. And the cool thing is that you don't need any feedback. Because everything is known, the growth is known because you're prescribing it. It doesn't require any feedback, but you just need this relation. And so this is the result. So in this case, we took a flux that should give us a 5-fold shape. And so then we made sure that the pressure was giving us fluxes that matched the theory. And maybe it's harder to see, this was the result. And actually, this was done by a student of Peter's. We actually played a trick on him. We didn't tell him what to expect. And so you can see the emergence of a five-fold shape, just like predicted by the theory. Not as pretty as a theory, because the theory requires you to get very big in order to have this nice, very symmetric shape, but nevertheless, you're picking the fingers. So the trick we did for the student, Jake Fontana, is that we just told him, do this. And he did it over and over, and he came back and said, it's not working. I always get the same five-fold symmetry. No, we were very happy. So you can get other symmetries. So now we said, now let's use a bigger flux constant, and we should be able to get an eightfold shape. And in fact, that's what happened. So these are 1 centimeters in radius. And so now, again, it's not as nice a shape as we would get from our simulation, but nevertheless, we're getting kind of a proof of principle of 8 fingers. We're able to control it. The challenge is that as we want more symmetry, or more fingers, we have to increase the flux coefficient C, and that makes the evolution faster and also makes the perturbations faster. And it takes a longer time, at least from the simulation point of view, to get to that shape. And so then that leads to a question, can you use other mechanisms to control the shape? And there was work by Martin Bazant's group that said, well, what if you use electric fields and you use electrolytes, basically as fluids? So they were using oil and water and glycerin with salt and various other things added. And so then the idea was, can you use the electric field together with viscous fingering, and that gives you another control knob, and can you get that to work? And so this actually now relates back to the last talk with this electric double layer, where basically what's happening is that when the electrolyte is in contact with the glass, so up here, the ions are dissociated, and the glass tends to be negatively charged. And so then you have the ions in the solution, and they accumulate near the glass, and that's what forms this kind of diffuse electric double layer. And then by now applying an electric field, you can actually make those ions move, and that creates an electro-osmotic flow that can act together or inhibit the pressure-driven flow. And so, for example, why might that work if you set up your electric field so that you have, let's say, an injection, so the pressure is driving fluid this way, and you set up your electric field so the ions want to go the other way, then you actually increase the resistance to invasion. And so what effectively that is, and Bazant's group, they termed this a electrokinetic thickening. So it's like an apparent increase in the viscosity of the fluid that's being injected to, right? And so and so that decreases the instability. That can decrease the instability. And so they actually did experiments and demonstrated that indeed this can happen. So you can take a case, for example, here, this is 0 applied field. And so this case is where the fluid being injected would be stable. So this is like a viscous fluid going into a less viscous fluid. And as opposed to the other way, and so that's stable. But with the electric field, they can make it unstable if they take it the opposite direction, so it goes together with this guy, or they can make it stable by this thickening process. And then they can take something that would be unstable, so less viscous going into more viscous, and then they can stabilize it by taking the right applied field. And so their basic mechanism that they described was like this, that it's this electro-osmotic field. And so now what we want to do is we want to characterize this. So they did some examples, and it's hard to do too much with at least with their experimental setup, but it was nevertheless a proof of concept. But what we wanted to do is fully characterize the system and then see if we could actually control the shape. They were talking about stabilization. Can we actually control the shape? And so now what you have is, in addition to Darcy's law, you have this electro-osmotic flow where you have an electric potential and now an electro-osmotic mobility. And so the total velocity is the sum of these two. And you have a current that comes from the pressure-driven flow and a current that comes from the electro-osmotic flow. And so the total current is the sum of the two. And then the fluid is incompressible, so you have divergence U is 0, and then you have divergence of I being 0, so no net charge in the liquid. And then in the interface, we have that the potential is continuous, but the pressure still has a jump. And then we're prescribing the injection flux, and we're prescribing the applied current. And then if the Debye length, since the Debye length typically for these double layer is small, much smaller than the gap width, the idea is hopefully the Hele-Shaw approximation should still be good for this, for the electric field. And given Bazan's group's work, that seems pretty likely. And then again, now once you've solved for the velocity, then you can move the interface and you repeat the process. And so then you're applying so you have electrode at the center as well as on the edge now. And so now we'll do the same type of thing. It's much more complicated than the simple Hele-Shaw flow, but we'll do the same thing. So we take our, I should have put this picture up before, but we take our interface, we perturb it, and then we look at the evolution of the perturbation and really the shape factor, delta over R. And so n here, sorry, n is the wave number, not k now, but n and k are, so this is the wave number of the perturbation n. And so this is, a particular combination of the electro-osmotic mobility and the hydraulic mobilities and the different fluids. This is the flux term, so this is if this were positive, that's the driving force for instability. And then this I is the current, and this is the surface tension, the stabilizing guide. So you can see all of those coefficients come into the surface tension term. And then you can, if you now take the derivative with respect to n and set that to 0 and solve for n, you'll get the maximally growing mode. And then there's a formula for it. And so if you want to preserve the current, if you want to preserve the shape, so I want to make this guy 0, then I can choose the current I to do that, and then the I is related to everything else through this formula, just the same way that we did for the simple Hele-Shaw. But now we have a relation between the I and J. And then at the fastest growing mode, you get this formula. So if you stick in, you want the fastest growing mode, you stick it back into the linear equation, you'll get this equation. And so what's interesting is that there's no condition on the flux. The flux is whatever it is, and then you determine this specific current for that particular flux. Now, what you observe over here, though, is that this term comes with a 1 over r cubed. This term comes with a 1 over r squared. So if I took the flux to be constant, this is still the fastest growing mode, but if I took the flux to be constant, when this thing eventually grows, when r keeps growing, then this term will go to 0 faster than that one. And so eventually, if the flux were constant, this one would beat that one. And so you'd always have stability. So everything would grow like a circle if it gets big enough. And so instead, what you want is something where you have an instability. And so you don't want to take a constant flux. And so, and if you took a 0 flux, then of course the radius would be unchanged, this would be 0, and then you just have this term. And we can identify a critical flux, which is basically making that if we had basically going this 1 over r, that's going to make this guy 0. And so that's our critical flux. And just like we had for the standard Hele-Shaw. And so now if we took the flux a little bit less, so if you take the flux a little bit less than this, then you can have instability. Okay, and so with that as a guide, then we developed a numerical method. So I'll just kind of go through this quickly, which is that basically we use potential theory or boundary integral methods to solve. So we don't solve in 2D, we just solve for an interface. And then we track the interface, and now we have these two potentials. The velocity, one is really a velocity potential, and the other is this electric potential. And then we can solve these coupled integral equations. So they're second kind Fredholm integral equations. They're relatively straightforward to solve using GM-Res. And then you can construct the normal velocity from the derivative of this layer potential. And then we have to do some numerical tricks to try to keep things stable. And so this is based on some really old work now that we did, where we can introduce this particular tangential velocity, because we have freedom to do that, so the points don't cluster, they can remain equally spaced. And then we can use a standard time stepping methods. But here is also another key advance. And so we want to grow these bubbles or drops basically in the Hele-Shaw cell very big. And so the problem is, if you recall, the flux scales like 1 over r. So as the thing gets bigger, the flux is smaller, so it grows slower. And so if you wait and you go on just the normal time scale, it will take you forever to do one of these simulations. So instead what we do is we introduce a rescaling. So we rescale time and we rescale space. So we keep in our numerical calculation, we keep the interface the same enclosed area. And then we rescale time basically so to speed up or slow down depending on the process. In our case now, since we're growing, speeding up. But if you do shrinking, you want to slow it down. And so then you can write the velocity in this scaled frame and rescale all the variables. And in this rescaled frame, the area of the enclosed interface is constant. And in this particular simulations I'll show you, we're going to take this rho bar to be r squared, where it's the size. And so this will give us exponential growth. So in the rescaled frame, we'll have the radius grow exponentially. And then we can rescale, let's see, I think I went the wrong direction. So then for our numerical method, what we have to do, we have an interface, so now we're going to discretize it. We'll use pseudo-spectral methods. To do that, we'll use spectrally accurate discretizations to approximate the integrals, second order atom smash forth in time, and then we'll remove the stiffness that comes from the surface tension using a version of the small scale decomposition. And then this is a set of parameters for a particular set of experiments that was Bazan scripted that I showed you very early on. Okay, so now with this method, we can then look at convergence. And so just to make sure we're accurate, these are some of the simulations. So this is what we're doing is looking at convergence in the area. So the area should be fixed, but it might be changing a little bit. And so as a function of this rescaled radius, we're plotting the error. We first do it, change the time step to make sure it's accurate in time. in this, you can check that this ratio is, but it's log scale, but it's indeed second order in time. And then in space, what we can do is we go and successively double the number of points, and we can see everything is recovered. But then if you lose resolution, the error drops. But then when you go with the higher resolution, everything matches, and you can go farther in time. OK. You can also check against the theory, which is good because we need to do that because it's so complicated. But again, here's our linear theory. And then what we can do is measure the nonlinear for the shape perturbation. So you can write down the solution of that simple linear equation. And then you can construct the nonlinear shape factor, which is basically the perturbation relative to the effective circle. And so that's the solid, the dashed is the linear, and so indeed they're matching, at least at relatively early, small radius. And so that's good. And this is the deviation between the shape, the shape factor, the numerical one, so the nonlinear one, and the linear theory. And the deviation between the two is second order. So it's a line, so that everything is matching. So our numerical method is converging, and it's matching the linear theory. So we should be able to trust it. OK, and so now what we can do is we can look at the electro-osmotic flows now with this method. And so what we're doing is we're taking different currents. And so in this case, so here first, let's suppose that there's no electric field. And so this is the simulation with no electric field. And that's going to be our base. And then what we can do is we add an electric field, now a current. And so this will, taking it to this scale where this guy is coming from the linear theory. But this one is stabilizing. And it looks unstable, but you have to compare it to this guy, right? So this is more stable. The overall perturbations are smaller than this. And then this one is the destabilizing current. And why is it destabilizing? It looks simpler. Well, in fact, it's pinching off. And so it's changing topology. So in fact, this is what it's doing is getting these very narrow necks and then with a drop in the center. And so we can actually get this topological, this seems to happen, create a topology change in finite time. And so, so again, this is the radius as a function of the inner radius, so the inner region. This inner region as a function of time, we'll measure through R. And so in the stabilizing and the no electric current case, it's growing together with the radius. But in this guy, it's actually shrinking, although it doesn't shrink to 0. And this is just the velocity at that point. But you can actually change the surface tension. And so if you reduce the surface tension, so the previous one was 10 to the minus 2. If you make it 10 to the minus 4, then actually it will seem to pinch off. And that this is the corresponding evolution in that unstable case. Now you can actually look what happens if you don't do any injection. And so that means that the area is going to be fixed, but now we have the effect of the electric field. And so it's an area conserving non-local interface dynamics, non-local through the electric field. And so what you can see here is 2-mode, 3-mode, 6-mode, and 7-mode. And so what's happening in the 2-mode, this guy is the initial condition is being pulled down, and this is creating 2 pinching off drops. Then this guy is pinching down, creating this 3-lobed behavior, and then analogously here. And here it seemed to trap something in the center. So in fact, here these guys are actually pinching off just due to the electric field. And so you can look at the inner radius. The inner radius in here, as well as here, they're going to 0. And you can calculate you can fit it to an algebraic law where you can estimate the critical time at which that radius goes to 0. So it seems to be going to 0 in a finite time. So the electric field can drive pinch-off in a finite time in this model. And so you can also look at the effect of this destabilizing current. And so you get a power law behavior as a function of this measure of this current. So this is the time to pinch off as a function of the current, and it's the bigger the current, the faster the pinch off occurs. And the opposite trend with the surface tension. Okay, so that was just a bit of an exploration, just to see what's happening with the system, and now can we actually specify the shapes? So now what we'll do is we'll say, let's try to make this a 7-fold shape to be dominant. So we're going to choose we want this to choose the current and the flux so that the 7-mode shape is the fastest growing. But we have flexibility, right? Because there's that relationship we had from the linear theory, which said, whatever J we took, we can find the I, the current. And so we can introduce very simply a 1-parameter family. So we'll introduce alpha, so that our flux is going to be proportional to that critical flux that's making the shape perturbation not change. And then we can construct the corresponding I. And so we're taking a little bit less than that, so the system will grow. And now when you do that, this is the evolution. Very much like what we had before. But the cool thing now is that we have an extra parameter. We have this parameter alpha. So if we actually plot this shape perturbation as a function of radius, we can do that for different choices of alpha. We can always get these 7-fold shapes, well, within some range. But we can change the alpha and still get 7-fold shapes. And so this is again, the size. And these dots basically are kind of indicating where the system has converged to the limiting shape, the attractive limiting shape. So and then the height, so how far up you go, is measuring how perturbed it is. So if you're very low here, and so that is this guy, 0.49. It has 7 fingers, but it's not very perturbed. If you go up to 0.23, which is, I think, this guy, it's very perturbed, and you see this clear emergence of the shape. But now you can see when are you reaching this shape? Well, you reach this shape, well, all the way at 10 to the 36, so super big. Again, that's scaled, but it's still super big. But you can get it way down by changing alpha. So this gives you an extra control parameter. So now you can get the shape, if you choose this alpha, to be maybe 10 to the 5th. Still big, but now it's, a lot of order of magnitude difference. And not only that, you can control, with this parameter alpha, you can control the perturbation size. And so with this extra feature that you didn't have in just the standard viscous fingering, you have this extra knob of control so that you can control, and at least to some extent, when this shape emerges and how perturbed it is. And interestingly now, as you're taking alpha smaller and smaller, that's like taking J going to 0. And that was the case we looked at before, where we were getting pinch-off and very unstable behavior, depending on the sign of the current, or applied electric field. And so indeed here, if, for example, you go below a critical alpha, then what can happen is that you don't go to self-similar evolution anymore. Instead, you can get pinch off, just like we got for the j equals 0 case. And then what happens? Well, what happens is that the current gets to be the other, so instead of stabilizing, becomes destabilizing. And so then that's why you have this transition at a critical value of alpha, where you go from stable to unstable currents. And you can do the same thing for other modes. So you can do, for example, for 3 modes. And so you can get, these are self-similar shapes, but then you have the same problem if you start making the alpha too small, then you can get cases that won't reach equilibrium, they'll want to pinch off. And so this is this is now what happens for all of these different modes. So here we fix the alpha, but now you can change all of these different modes. This is like a morphology diagram in a sense, where this one is this guy. As you continue to go up, then you're getting these essentially limiting shapes where which is much more like the viscous case because we fix the alpha. And so, so with choosing the different maximally growing modes, we can choose the fix the alpha, and then you choose the current, and so you're varying the current in time, and then you can the system will converge to those limiting shapes. So to conclude, basically what we did is we looked at the Hele-Shaw cell, we introduced this electric field, and we showed that it can destabilize or stabilize the system depending on the sign of the the direction of the current. And we used that, so we investigated it, but we in particular used it to select the maximally growing mode, so to control the shape and to control the symmetry. And the nice thing is that having this extra parameter, and there was this, I mean, we just wrote it as a 1-parameter family. You could have many other choices, and this would. This gives us control of how long it takes to get there, and also the size of the perturbation, at least to some extent. Now, there's supposed to be, so I was supposed to touch on randomness, and I didn't really do that, but I kind of hit it a little bit in that very early result, just for the plain Hele-Shaw, where we varied the initial shape. Right, I took these different initial shapes. So one of the roles of randomness, I think here, and this is one of the things we tried to do in the experiment with some kind of limited results, is that the more random the initial shape, the faster you go to the limiting shape. Because in order to go to the limiting shape has a particular symmetry. So if you don't have that mode in the initial condition, it will take a long time for that mode to be nonlinearly generated. Whereas if it was in the initial condition, it would be fastest growing from early on, and it would tend to that shape. And so from our point of view, actually, if you want to get these shapes quickly, you should, one of the mechanism doing that, it would be to take into account, if we could actually generate random initial shapes, if we could jiggle the thing a bit, then it would actually help the system. And how about the future? So in the future, well, we just chose one particular choice for the flux, but one could do others. And then this kind of gives a pathway for doing other multi-field-driven interface problems. So for example, in the Hele-Shaw context, you could imagine you could apply magnetic fields if you had a ferrofluid. And people have done that, but not thoroughly to this extent. And so, but there's other kind of features one can add, and we didn't take into account any particular properties of the interface where we could have charges on the interface and so on, and that would give you more even more flexibility. So with that, let me stop and take any questions.